Welcome to our training session focusing on system components. Today's presenter is Don Gillis. Please note that you will be able to access the audio of today's presentation through your computer speakers. Following today's presentation, a recording will be available to you on our contractor resources and HVACR training pages on our website at climate.emerson.com in a few days. In addition, we will be providing you with a certificate of course completion following the event via email in a few days. Our session will now begin. Don?
Thanks, Kara. Well, thanks for joining us, everyone. Hopefully everybody had a good weekend. We went through these events step by step, and I told you at the beginning from last week that we'd progressively move along and get harder as we go along. Again, this is going to be kind of a refresher for most of you. We're going to be talking about additional system components. And like I said, we covered the 4 basic components earlier. Now, each OEM and system application will determine what accessories will be used. First of all, my name is Don Gillis. I think if you've sat in on a few of these already, I'm going to save you the long speech here, but I've been in the industry just about 28 years. I've been with Emerson just under 3 years, July of 2017. I work in educational services. I am a full-time instructor and a licensed journeyman and a couple other things. We'll get to the start of it. I slid this slide in this morning, and I sent it back, the presentation back to my coworkers back at Emerson to tweak it a little bit, but I thought this would be important. If you wouldn't mind, you can wait until you get the presentation, or you can jot this down now. I would highly suggest writing down Technical Help Guide. This is a free guide. This actual guide that you're looking at here, I actually Googled this. If you just put in Technical Help Guide in the Google machine at Emerson, it will pull this up. And the reason I thought this was important this morning is because as we go through this presentation, when we deliver this live on the road, we've already set where we have page numbers at the bottom of each slide. So I'm going to be referring to those page numbers, and that's where you're going to be able to find that particular slide or that information about that component in our Technical Help Guide. So typically the classroom would, all the technicians would have this book, and I would tell them to refer back to that page. So I thought it'd be nice to slide this in and give you a visual. Again, you have access to this online. You can print it out, make as many copies as you want. I can assure you that if you were to read this every 15 minutes, or 15 minutes a day, 15 minutes a week, whatever time you have in your truck while you're waiting for your next call or whatever that looks like, I can almost assure you you're going to get a raise. It's a very, very informational booklet. Very, very good. So here are the components, just some of them. I'm going to walk through them in no particular order this morning or this afternoon. And we're going to talk a little bit about what they do, what they're called, identifying. Typically, when I present this in class, the student would have a blank sheet, and they would fill in those numbers and identify each one of those components. We do this also with our CO2 trainer when we travel around the U.S. and Canada. We have our CO2 trainer, and we have them identify each components before we actually go out and look at it in the lab. So, again, in no particular order, we're going to start going through them one by one. We're going to start with the TXV. There's a lot of different metering devices. This just happens to be a thermostatic expansion valve, pardon me, okay? And we're going to walk through that. The only purpose for the TXV is to control superheat. And let me repeat that. The only purpose for the TXV is to control the superheat. Now, it does cause a pressure drop. All metering devices do. And like I told you last week, we have to have that pressure drop. So the purpose of the TXV, again, is to control evaporator superheat, and it responds to temperature and pressure only. There's some myths out there. What it doesn't not control is air temperature. It doesn't control head pressure. It does not control capacity, and it does not control suction pressure. It controls the temperature, pressure, or the superheat, okay? You can see by this chart here, the bulb on the top there is what we call the P1. The P4 is your high pressure subcooled liquid on the left. On the blue over here, let me use my pointer here, This will be, this is a closing force. This is your evaporator pressure. This P3 is your spring, okay? And that's what you would set your superheat if it was an adjustable type, okay? You can see the refrigerant pushing down here, going into the low pressure liquid flash gas, all right, as it comes through. This bulb typically has refrigerants. A lot of times it's the refrigerant that's actually being used in the system. Again, the P1 force is this bulb, okay? You have a diaphragm, stainless steel right here, and then you have a buffer plate. So the warmer this bulb gets, it's beyond the evaporator, as we all know. The warmer this bulb gets, it raises the pressure, okay, it raises the temperature, which raises the pressure, pardon me, and pushes down on that diaphragm and letting out more refrigerant into the evaporator, which cools it on the backside, leaving there, okay? When you're adjusting a TXV, if it is an adjustable type, clockwise raises the superheat. In other words, if you were looking at the bottom of this and you were turning right clockwise, that would be tightening this up and letting less liquid refrigerant or less saturated refrigerant through. Counterclockwise lowers the superheat, therefore letting more refrigerant through. That is referred to as the P3 closing force. Again, 1, 2, 3, and 4, okay? And you'll see later why I'm pointing that out to you when I come to the end of this. The thermal expansion valve, the inner bleed port, allows high and low side system pressure to equalize during the off cycle, thereby allowing the use of a low start torque compressor, two pole, okay? A bleed port is an internal passage directly between the valve and the inlet, okay? On shutdown, again, it equalizes and allows for a lower torque startup. The valve feeds too much. Just a couple things they put in here about, I wasn't going to get into a lot of maintenance and things like that and troubleshooting, but just one thing I think is very important. By the way, if you have a question, save them for the end of the presentation. Put them in the chat box, and I'm sure we'll have time at the end, and we'll address those one by one as they come in, okay? The bulb should be clamped on a horizontal run, if possible, and bulbs should be located on the pipe at the 12 o'clock position on 3/4 inch pipe or smaller, 8 o'clock or 4 o'clock on 7/8 inch pipe or larger, okay? And I'm not going to lie to you here. We print this out at the 8 and 4. If you were to look at Danfoss's literature, they may tell you 9 and 3, and I shouldn't even say may, they will, okay? But where we don't want this for sure is at the 6 o'clock position because of the oil, okay? So we're trying to get an accurate reading of what that's doing there. In all cases, that bulb should be insulated from the ambient temperature. It should be really tight on there, and use the proper, whatever comes with it, whether that be brass or copper, put that on there. Don't use duct tape or Panduit straps, and obviously I'm joking. This has got to be a clean surface also. We want a good contact there to get a good reading. Valve feeds too much in case the bulb and equalizer. In most cases, the bulb can be mounted in any position on a vertical run. This is best, okay? This is okay. It is not true that charge will leave the bulb if mounted with the cap tube down, okay? Valve doesn't feed enough, causes of it. The loss of P1 means the only opening force in the valve has disappeared. Again, this is P1. This means little or no flow through the valve, high superheat. Diagnose, remove bulb and hold in your hand. If no change in the valve flow, then the bulb has lost its charge, okay? Again, P1 is an opening force, P4 is an opening force, P2 and P3 are closing force, and I always like to put this on the board when I'm teaching. P1 plus P4 equals P2 and P3, okay? Now, corrective action, replace the power head. If it doesn't have a power head, then you'll have to replace the bulb all itself, okay? This is the future. This is what you're seeing a lot of it. Even 4 or 5 years ago when I started to get out working around things outside, expansion valves were starting to become very common even in residential equipment. Here again is that page 14, that note in the corner here. That's referring to that technical help guide on page 14. You can see how quick this is, the wide range. Electric EEVs are so much better. They're faster reacting times. This thing can go from 0 to 2,600 steps in 5 seconds, okay? It moves very, very quickly. I've got a little video I'm going to show you. It doesn't have sound, but you can get the idea of it. This is the EX8 that's shown right here with 2,600 steps, okay? And you can see the different varieties and sizes up there, okay? Let's see if I can get this in place so you can hear it running. And this is what that looks like. All it's basically doing is sliding over in this teardrop, okay, and letting that out. And when that hole gets when the hole gets over this would be open all the way. As it covers here, it blocks it off. So as the more of it that's over that teardrop, obviously, the more refrigerant that's going to come through. Again, open to close in 5 seconds. All right. And things like our newer refrigerants, especially like CO2, for example, and I know I keep going back to that because I teach a lot of it now. CO2, you're going to see a lot more in your supermarkets, obviously, because of the EPA ruling that's coming out. It's very hyperactive, so you need everything electronic. Everything's got to be modulating. It's a whole different animal. This just shows the mounting position of an EX valves. This is preferred. This is acceptable. What wouldn't be acceptable is this motor on the very top. And this is typically when I would ask the students why that would be. And the answer is for lubrication for that motor, okay? We would never want that up on the top, okay, vertically up. It should be down or to the side here where we can get some lubrication. EPRs, evaporator, pressure regulator, okay? It is, so there's two things here. This could either be a crankcase pressure regulator or, pardon me, an evaporator pressure regulator. The way we identify that is this is a little Schrader valve. And what the EPR is doing is keeping the pressure on the evaporator the minimum temperature, okay? That's what it's doing. And what it does when we set the pressure of something, we set the temperature of something when it's saturated. And in the evaporator is saturated refrigerant. So if we want this evaporator to be at a certain temperature, let's say 45 degrees or 35 degrees, we would then set the pressure for this to stay there at the minimum, okay? And this is how that works. The refrigerant comes through. Again, the Schrader valve is always going to be, if you see one of these are directional, flow directional too, so you have to look at the arrow on the side of it. This Schrader valve, wherever this is at, that's what it's going to identify what it is, whether it's an EPR or a CPR. If it's closest to the evaporator, this is an evaporator, an EPR, okay? So the refrigerant comes up through here. What you're doing is you're adjusting it with this cap off down here. You're turning that and tightening up that spring to allow setting the pressure as the unit's running on that evaporator, which then sets the temperature. You'll see later on that you can set these in supermarkets, and you can do one for each evaporator, if it's a medium temp, low temp, or whatever that looks like. IPR just refers to its function as an inlet pressure regulator, okay? And it comes through there, again, down towards the compressor. Here's that example I was telling you about. You have one set here for 20 degrees, minus 20. I typically in class would have someone pick out a refrigerant like 404A and then have them take a few minutes and tell me what the pressure would be set at each one of these coalition with the temperatures that we're setting this for like 404A. So, and this may not, you in a supermarket or something like that, you might have something here one day that you want it to be 35 degrees, and then maybe you need more room for something at minus 30, you can adjust this and then make that into a 30-degree walk-in if you would like, okay? Each EPR valve is set to the pressure corresponding to the saturation pressure from the temperature setting desired. Systems with defrost, I wanted to note, have an EPR valves on each evaporator. Systems without may only have a check valve on the lowest temperature evaporator outlet set to the EPR valves. You adjust superheat. And be sure that any external equalizer, TXV, is tapped in the evaporator on the side of the EPR. In other words, beyond it, okay? Crankcase pressure regulator. You can see where this Schrader valve has changed, okay? Now it's right here. So when you see that in the system, and this happens all the time, you may not see both of these in the system, by the way. You may have one or the other, okay? All right, so when you walk up to a system, you have to identify where that Schrader is, because the side you're taking the pressure on is the side we're focused on. So in this case, it's the crankcase pressure regulator, and it's used to regulate the crankcase pressure. It closes when downstream pressure is too high, causing high amp draw on the compressor. It will not prevent liquid floodback, however, okay? So this is preventing it. This is outlet pressure. When we were talking about the EPR, that was our inlet pressure. This controls the pressure downstream, okay, if it gets too high. Same thing on the CPR, or outlet pressure regulator, OPR. The inlet pressure is balanced because the effective area of the bellows is the same as the seat area. Again, it comes the same way. Now notice where this is at. Now it's up instead of up against this. And the purpose of that is if it's coming down here and the pressure gets too high, okay, it shuts itself and closes down, all right? Talk about suction line accumulators. Suction line accumulator prevents liquid refrigerant from returning to the compressor. The accumulator must be sized properly to ensure the oil return on the compressor. Helps prevent liquid flood back, and you'll always see these on a heat pump. I've never not seen one on a heat pump. They'll always be there, okay? Again, it's just another way to protect, along with traps and sizing up your proper refrigerant lines to keeping that liquid refrigerant coming back to the compressor. This shows the cutout or the anatomy of one. You can see this on the left-hand side, the outside. The diagram I put in here I think is important, because if you're looking at this, those pipes almost look identical, like in depth, like they're both back the same depth. But in actuality, if you were looking down on it, you would see this A is offset to B, okay? So the gas is going into A straight down, all right? And that allows the oil to drop down to the bottom of it. The only thing that goes in B, the other side of B, this J tube, okay, is actual vapor. The oil drops out because, again, we don't want that oil or that liquid refrigerant going back to that compressor, liquid refrigerant going back there, okay? So what we're going to do is, as this vapor sucks through here back to the compressor, we've got a very little pinhole here pointed out in C, okay? And you'll usually have some, liquid refrigerant oil down here at the bottom. That will trickle through there and allow just a little bit of it to come back at a time, as opposed to if you've got something, let's say bad airflow across your evaporator, coming back down through there and going directly into the compressor by itself, all right? Suction filter dryer, okay? I put an AE bulletin in here. We talked about our apps last week a little bit. This is our Engineer, our AE app, okay? If you don't have it, please look it up. It's free. It's very useful knowledge. This is AE Bulletin 24-1105. The suction line filter dryer used to clean a system after a burnout or has high levels of activated aluminum to remove acid. It also filtrates smaller particles, okay? But unlike a liquid line filter dryer, it removes mostly your acidic, okay? It is used on a clean out after a compressor is burned out. It should be watched closely and removed after a maximum of 48 hours or as directed as the AE bulletin. Once the system is cleaned, replace with a permanent type suction filter. Okay, so you never leave the block filter in here. All right. Suction pressure drop, we talked a little bit about in another presentation, how crucial that is on suction drop as far as the capacity of a compressor. This just shows you a nice visual of this would be the type of block filter we would put in there to remove acidics and particles inside of it. This is what we're talking about for the 48 hours, somewhere between 48 to 72 hours, and then remove. Now, if you do your testing on your acids and you still got showing acidic in there, obviously it's not one and done. We have to put a new block in there, and we might have to do this multiple times. Typically, one time is enough, but it's not sketched in stone. You have to keep testing the refrigerant after you remove this, okay? This is the refrigerant, the filter dryer that you would leave in permanently. This just picks up particles, all right? It doesn't cause near as bad as a pressure drop as a block does. This just shows the cutaway, all right? Obviously, this is the type that would be in residential. If you're in the residential world, you'd want to have some kind of ball stop on each side of this to do preventive maintenance, okay? Oil separator. Oil separator simply returns the oil to the compressor. You can see it coming back here. It separates. You saw how the accumulator was designed. This comes down here. Any oil that drops out the bottom, it helps come back to our mechanical oil. In this case, this is the OMB, okay? To prevent liquid return to the crankcase, a 2-minute time delay solenoid should be placed in the oil return line, sensing compressor current. Again, you can find more information about this on page 45 in your technical help guide that we talked about at the very beginning of this. If you have questions about any of this at all, feel free to email me directly at don.gillis.emerson.com, okay? This just shows us out in the field a picture we took of the oil separation. Some of the theories, the methods, we reduce the velocity, the coalescing, the change of direction, and the impingement, which means the oil might fall on a stainless steel mesh type screening device, centrifugal and helical. The velocity reduction is the major factor in oil separation. It allows the oil to fall out of the gas stream. All brands of separators provide for velocity reduction as well as incorporating change of direction and impingement techniques, okay? This is our OMB. It was originally our OMA. The A and B are just the revisions. We now have OMC, and this is what most everyone is going to now. And I'll show you, I think I have a video here that we'll try to play for the new OMC we've had out for about an hour now. They're more reliable than just a mechanical oil level. It provides an alarm, annunciation, and compressor shutdown. And it allows for remote diagnostics through your E2 controller. So if you're in the supermarkets and you deal with E2s, this can be tied into it. Also in your core sense, the solenoid valve is energized to fill the compressor when the oil level drops below the float actuator. And this has a little ball float in here. I don't know if you can see it or not, where the oil is. And when that gets below there, it turns on and brings the oil back. See if I can get this to play for you here.
The OMC oil management control from Emerson maintains a proper oil level in the compressor crankcase and is recommended for multiple parallel compressor applications. The OMC is available in 120-volt and 240-volt models, eliminating the need for a step-down transformer, which is often required when using a 24-volt control. Special models are also available for transcritical CO2 and ammonia applications. The OMB oil management control is available in 24-volt models and is suitable for subcritical CO2 applications. The Emerson OMC is easy to install and serves as a drop-in replacement for multiple compressor types and manufacturers. Just select the appropriate adapter, which is sold separately. All wiring is easy to access with a removable front cover. The conduit connection can be made via side knockouts in the self-contained electrical enclosure designed to maintain proper code compliance. The terminal block provides simple connections. The OMC also provides easy field monitoring. The optional dual-side glass provides oil level viewing from multiple directions. The float ball in this glass enables visual indication of the oil level. Tricolor LED status lights clearly communicate how the system is functioning. A green light signals the oil control is receiving power and the compressor is a proper oil level. The yellow light indicates the control is currently supplying oil to the compressor crankcase. And if the red light is lit, the control prevents the compressor from operating because it has failed to reach the proper oil level after 2 minutes. The control will continue supplying oil, and the alarm will automatically reset when the proper oil level is reestablished. If 5 alarms occur within 30 minutes, the compressor lockout feature is enabled, which requires system diagnosis to prevent compressor failure. To learn more about the Emerson OMC Oil Management Control, visit emerson.com/OMC.
Introducing the Copeland.
Sorry about that. All right. Hold on 1 second. For some reason I'm getting something wrong.
And more reliable in operation.
Falling apart on me. Okay, let's talk about hot gas bypass and solenoid valve. The purpose of the hot gas bypass. You're going to have to excuse me for 1 second. For some reason, I can't get this. There we go. So sorry. I really am. All right. Hot gas bypass and solenoid valve. Hot gas bypass, it helps maintain a higher suction pressure in the evaporator. So basically what this does is when it's really, really cold outside and you don't have much of a load outside coming through, this pressure is going to drop. It's going to react almost like poor airflow, and then you have the possibility of liquid refrigerant returning back to the compressor. What this does is it pumps in refrigerant from the solenoid valve. A solenoid valve is nothing more than on and off, open and close. It opens up, okay, and meters through here, sends it back down through here, and puts pressure on the evaporator, okay? Helps maintain higher suction pressure in the evaporator. The back pressure is regulated to maintain the compressor running during low load situations, and a hot gas solenoid is used for a pump down to isolate the suction side, which this is. This is the solenoid we'd use for a pump down, and we will talk more about that as we move along. You also can find this on page 41 on your technical help guide, and there is an A Bulletin 1160. Head pressure control valve, quite a few different names for this, headmaster. The normal route of this would be the C through R, okay? And what happens here is, again, the sole purpose or the main purpose for the TXV is for superheat, right? But we have to have a pressure drop here, okay? We have to have some kind of pressure drop, all right? So what happens if we get a outside ambient gets too low out here, and it doesn't, and it gets, our pressure gets too low in here, we start to close C down where the refrigerant's coming. What happens here is, if this pressure gets too low, we don't have enough pressure to go across the TXV to get a good pressure drop to make this refrigerant change into saturation, all right? We have to have a particular certain amount of pressure drop of whatever this TXV is sized for. So when it starts to get too low, what happens is it closes down C, okay, and opens up this hot gas, this discharge gas through here, and it takes over and comes down through R. Now, one would be thinking, well, this should be liquid refrigerant, but with the gas inside here in our receiver, it's saturated anyways, and it puts pressure on there, building up the pressure to be able to drop that, have a good pressure drop across our TXV. It also, when this gets shut down, starts to back up, okay, inside the condenser until you see where it starts to get purple here, okay? So it matches what's going on with the system and the outdoor temperature, all right? So your coil gets a lot smaller, in other words. We're rejecting a lot less heat. It maintains a minimum pressure in the liquid line. There must be an adequate pressure drop across the TXV, as I mentioned, to achieve full capacity. When low ambient conditions exist, the head pressure tends to drop. The normal route, again, is C through R. This just shows one up close out in the system. Again, it maintains a liquid subcooling and prevents liquid line flash gas. It can be used for properly to operate systems with hot gas defrost, a hot gas bypass, or heat reclaim. If you have heat reclaim, what that might look like is you might have, over here, you might have another a coil and some ductwork, or you might have this tied to a water heater of some sort that you can heat that water with that extra discharge gas that you have, okay? It provides sufficient pressure drop across the TXV is the main purpose for it in this application. And this is just a couple animated pictures I wanted to show you and the difference of how what this looks. So if we've got ambient temperature, let's say 100 degrees outside, again, our discharge gas is coming through here. Normal operation, we said, was C to R, okay? So the pressure on the condenser is 260 psig. So it's a higher pressure than outside. It's going to come in, go into the receiver, and everything's good, all right? Here's our receiver. You can see liquid at the bottom, vapor at top. Again, the receiver is saturated refrigerant. Now notice what happens when the temperature drops. Now we're saying the ambient temperature is 20 degrees. And what happens then? We get less and less of that condenser, condensed liquid out of the condenser, and more discharge gas mixing with that, okay? It opens up that plate, okay, that little disc there, and has higher pressure than the pressure that's in here at 84 psig, and it opens up and it comes into the receiver saturated. It's mixed in there. As the ambient continues to drop, the disc will move, this being the disc, farther away from the upper port and closer to the lower port. Less liquid in the refrigerant allowed in the receiver, which means more is backed up into the condenser, as we said earlier, further reducing the surface area for heat exchange, causing the head pressure to stabilize. All right. The receiver, quite simply put, is nothing more than a storage vessel, okay? In low load conditions, this might have quite a bit of refrigerant inside of it. On high load conditions, you might have all of it out in the system. It's just a place to store any extra refrigerant that you're not using at the time, okay? A liquid receiver stores liquid refrigerant from varying loads. It's used to maintain a full column of liquid to the metering device, and OEMs will typically size and install the receiver based on the system design. This just shows the nice anatomy of the receiver. Notice the dip tube down here reaching to the bottom, okay? One tube connects to the condenser outlet, and the tube with the service valve over here connects to the liquid line, all right? Again, we have an AE bulletin here. I would highly recommend looking into that. If you haven't loaded Copeland Mobile or the AE Bulletin app, please do, especially the Copeland Mobile. You can get to the AE Bulletin app through Copeland Mobile. Again, that app is free, and I don't care if you do HVAC or if you do refrigeration, it will help you immensely, okay? It is like the cheat sheet, if you will, of what we used to have to do all the math for. Now it tells you everything by itself. Liquid line filter dryer, possibly the most important thing in the system, okay? Our best friend, if you will. When removing this, I don't want to get too far ahead of myself. When removing a liquid line filter dryer, we want to cut them out, don't braze them out. The majority of the reason this is in here is to remove moisture, isn't it? When we add heat to this, all we're doing is pushing steaming that water that you've already caught back into the system, putting a new liquid lined filter dryer in, only to catch the same moisture that we already had caught. So when you're removing this, please remember, please cut it out. Don't sweat it out, all right? Unless you have a flared fitting type, and that's a different story. You don't have to worry about anything. You can find a lot of information, again, in that technical help guide, page 26, system protectors, okay? When do we change a liquid line filter dryer? The first and foremost, we change a liquid line filter dryer anytime the system's open. Anytime you open the system, you need to change the liquid line filter dryer. If you have a pressure drop across a liquid line filter dryer, okay? Let's say around 4-pound drop. Some people say 3, some people say 4. Somewhere around 4, I think, is a good number, okay? And I'll explain a little bit more about that here in a little bit. I want to share with you that I found out, that I learned since I've been here at Copeland. The other thing is a temperature drop, okay? Extensive temperature drop. There really shouldn't be a lot of temperature drop across this. If you see something frosting up, which I've seen before myself on a liquid line filter dryer, obviously that needs to be changed, okay? But in all actuality, if you take a temperature reading on both sides of these, the difference should be very minimal, if any, okay? Here again is the 75% molecular sieve. Molecular sieve is what we use to remove the moisture. The 25% is activated alumina. That's what you'll find in removing the acidic stuff. So when you're talking about suction filters, this literally would be flip-flopped. You would have 75% activated alumina because a suction filter is main purpose is to remove acidic, and then you would have the 25% molecular sieve, okay? You can see the different colored beads in here. That's the majority of those beads is for the molecular sieve, and the lesser of the two is the activated alumina, okay? I want to talk about one more thing that I told you I learned since I've been here at Copeland that I did not know. Let's say your pressure drop is somewhere around 4 pounds. You come up to it. I want you to keep in mind a handful of years ago, just a couple years before I started here, Copeland bought all of our competitors' liquid line filter dryers and ours, and they tested them. What they found was, it's straight out of the box, a brand new liquid line filter dryer typically will have somewhere between 1.5 pounds to 2 pound drop across a brand new filter. So when you're changing these out or you're checking these out, if you have a way to check pressure on both sides of them, if you have the kind with the ports on them, keep in mind that out of the box new, you've already got about a 2 pound or 1.5 to 2 pound pressure drop across it, okay? See if I can get this to play for you.
This demonstration, we're going to prove that not all filter dryers. The three main functions of a filter dryer and a refrigeration or air conditioning system are to remove moisture, remove acid, and to remove solid particles. The Emerson EK filter dryer has a compacted bead construction which features best-in-class filtration. This demonstration closely replicates the ASHRAE procedure for testing liquid-lined filter dryer filtration. By filling the receiver tank with refrigerant in this closed-loop system, we simulate the conditions present in an air conditioning or refrigeration system. First, we'll install a competitor's solid core filter dryer. Starting up the system, you'll see the liquid refrigerant entering the dryer, passing through it, and then being recycled and pumped back through the system. We'll now add roughly 5 grams of solid contaminant into the system. As you can see, the refrigerant is pretty dirty. The contaminated refrigerant is pumped through the dryer, then back into the receiver tank and through the system again and again. There are a few factors to consider when it comes to filter dryer filtration. First, the speed at which the filter dryer removes the particles from the system. The faster, the better. Second, total particle removal capacity. More is obviously better. Third, the ability to retain those particles. And lastly, the pressure drop across the dryer versus the amount of grit captured. Significant pressure drop is detrimental to system capacity. We've run the test for almost 3.5 minutes and the refrigerant is still really cloudy. Now we're going to simulate system cycling. Notice that upon startup, you see the release of contaminant back into the system. You can demonstrate the effect of normal system vibration by tapping on the dryer. There's a substantial release of contaminant back into the system. After more than 4 minutes of operation, the system is still very cloudy. Now we remove the competitor dryer and replace it with the Emerson EK. We'll leave the refrigerant as is. Whereas block-style dryers rely on the block to perform filtration, the Emerson EK uses a special 20-micron pad at the outlet. You'll notice that the grit isn't passing through the Emerson EK. The dryer captures the particles, and after only 50 seconds, the refrigerant is clear. Now we add another 5 grams of contaminant. You'll see how quickly the Emerson EK cleans up the system. In about 1 minute and 45 seconds, the EK cleans up not only the contaminant left in the system by the competitor's filter dryer, but also the grit we just added. When we start and stop the pump to mimic system cycling, the outlet line of the dryer remains clear, demonstrating that the EK filter dryer continues to hold the contaminants. By tapping on the Emerson EK, we simulate system vibration. Once again, the line remains clear, showing that the filter dryer is retaining the contaminants. For best-in-class 20-micron filtration, choose the Emerson Compacted Bead Liquid Line Filter Dryer.
All right, talk about sight glass moisture indicator, our eye to the system, okay? What can we see in the sight glass? Well, we can see discolorization of the refrigerant. We can also see moisture, what we were just taking out in the liquid line filter dryer. A lot of people used to charge by them. It's kind of hard to do that now in some systems with all these new blends and things, bubbles, okay? But you can see the moisture, you can see the cleanliness of the refrigerant, okay? Shows the condition of the refrigerant at this location. We want to ensure that the refrigerant is in a liquid state and dry. Think about this when installing a system. It's not a requirement in all systems. You typically don't see these in residential, but not a bad idea. I know guys that put them in on everything they install. From left to right, this happens to be ours, by the way, Emerson's. From left to right, you can see the way they're designed. Obviously, we're not looking for them to get wet. Anything in the caution area would cause us to want to look at that liquid line filter dryer, okay? You can see the colors that they are when they're wet, as opposed to when they look like when they're dry, okay? The minimum standard is 100 parts per million, and most of these are designed to set up for 75 parts per million. They start to show wet. Ours happens to go off at 50. Again, we're not looking for this to get into the wet area. If it's in wet already, it's went too far. When you see it start to enter caution, that's the time that you want to put the liquid line filter dryer. And I get this question a lot out on the road. Once you put the liquid line filter dryer, there should be no reason to change this sight glass. It will go back to being dry again, okay? I've never heard differently from anyone that I've ever spoke to, but anything's possible, I guess, okay? Liquid line solenoid valve. Again, liquid line solenoid valve is just a valve for on and off or closing and opening, okay? In this case, on a liquid line solenoid, this would be what we'd use to pump down the system, okay? We would pump down the system back to the, when we have like a off-cycle migration, like a flooded start, all right? We would pump this down, keep it pumping down. It's tied into the thermostat. As it comes in, goes all the way through the compressor. The compressor keeps running. The solenoid valve is shut. It puts it back in here into the condenser, also the receiver. We have a low pressure cutout that would cut this out. It would close it up and lock all the refrigerant over here in the receiver and or the condenser. When the set point changes a degree or the cooler gets 1 degree warmer, the walk-in cooler, this would then open and start putting the refrigerant back in there. The pressure cut in would go off, and the compressor would start back in, and so on and so forth. And that's the cycle of it to use for a liquid line solenoid valve and a pump down feature, okay? Again, if you do take me up on that offer of getting that technical help guide on page 21, you'll have all the information you need to know about liquid line solenoid valve. I guess that's all I had. I ran a little early today, and I'm sorry for the malfunctions that I had there. I truly apologize. Kara, any questions?
Thank you, Don.
You're welcome.
We will now take some time to answer a few questions that the audience may have. For the audience, if you do have a question, please utilize our question and answer chat box in the bottom of your screen. We do have a few questions to start, Don. The first question is, how can I set an adjustable TXV if someone has messed with it?
Set an adjustable TXV if someone's messed with it. So if you walk up onto a job and the TXV is misadjusted, or somebody's been messing with it, or if you climb up on a ladder and you see the cap inside and dropped off in a tray, for example, the way you should do that is run it all the way up, screw it all the way into the top, back it out all the way, and count the revolutions, okay? If you count from the top to the bottom 10, go back up 5. A real good rule of thumb, I don't like rules of thumb, but you would, halfway point is a manufacturer setting for most all set TXV valves, okay? So remember, wherever you're at, you want to start over at the beginning. If someone's been messing with it, which we don't encourage anyone to adjust them, leave them alone, okay? But if you need to adjust or someone adjusted it before you, take it all the way to the top, count the revolutions coming down, evolutions down. If it's 10, go back up 5 to midpoint, and there you should be right back at the factory setting. Good question.
Another question that we had was, could you briefly review the function of a TXV?
Yeah, briefly review the function of the TXV.
Mm-hmm.
Yeah, I'm going to go back to the slide here. It'd be easier for me to show. Bear with me here just for a second here. We're all the way back here. Okay, so again, most of the time, not all the times, we have the refrigerant that's actually in the bulb that's in the refrigerant. Let me go back one more time. Let me see this one. Maybe this one better here. So this typically has your refrigerant that's in the system, okay? And it's reacting above temperature that it's fastened to on the refrigerant line. So P1 on the top is an opening force, okay? As we move along here, on the right-hand side, P2 is pressure being pushed back from the evaporator, all right? P3 is your closing force, which means nothing more than your adjustment. Again, clockwise, you're tightening up or letting less refrigerant through, liquid refrigerant through, okay? So when you go clockwise, you're raising the superheat. Obviously, you're getting warmer on the backside of the evaporator. And then we have our liquid line coming through here, which is another opening force, all right? So P1 and P4 are opening forces, and then you have P3 and P4, or pardon me, P2 and P3 as closing forces, all right? So P1 and P4, which equals 5, by the way, and 2 and 3 equals 5. And that's the way I always remembered it when I was doing this, okay? P2 and P3 equal 5, and P1 and P4 equal 5. They're your opening forces. Here is your closing forces, all right? And again, you're only detecting, besides causing a pressure drop, it's only their purpose for doing superheat, okay? Good question. Hopefully that answered it.
Another question that we had was, where can we find and download the technical help guide?
Go to the, what I did this morning was, the picture you're looking at, I literally went to the Google machine and put in technical help guide. Now, it may not have popped up the very first thing that came up, but you will find it. And if you don't find it, again, my email is don.gillis, Gillis, @emerson.com. I have it on a PDF on my phone, and I religiously email it to people when I'm along the road. If we don't hand this book out for a particular class, I just send it to them from my phone, and I will gladly do that if you email me, I promise. Okay?
Another question that we had was, what were the apps that you had previously mentioned?
Okay, the big one is Copeland Mobile, okay? And what I do is I just go to the App Store and I literally put Emerson in there. You can go to Emerson Climate, but I just put Emerson in there. You might have 15 apps populate, 12 of them are ours, okay? And just pick and choose. The biggest one is like a baby blue color. Let me see if I got something here I can pull up for you. Not sure if I've got one here or not. Well, anyways, I'm going to leave it that alone. It's baby blue colored. It's going to say Copeland on the front of it. It has an icon of like a little Wi-Fi icon. But just go to the App Store and find Copeland, put in Emerson, and it'll say Copeland Mobile. Again, it's like a light blue or a baby blue, okay? The other one is the AE Bulletin app. It has the letter AE on it and a little icon of a book, and it's Application Engineer Bulletins. So it's kind of the way Emerson sees, everything that's out there from Emerson, okay? It's also like a big Google machine also, for Emerson products. You can put anything in the search bar that you want. I commonly use the word torque in the classroom, and I show the technicians. I just put the word torque in there, and next thing you know, it pops up all the torque values of everything we make out there. It's really, really helpful. The other one that I would highly suggest, I guess depending on what you're in, if you're in refrigeration, the HVAC Fault Finder is a great app. It is literally like a flow chart of troubleshooting anything that's out there. Whether you have core sense or you don't have core sense, it's the bomb, okay? If you're in residential, I would get the E app, the E-Saver. It's short for Energy Saver. It is a great app for your customers to be able to pick and choose what type of equipment you're thinking about quoting them. It is a great app. Again, all these apps are free. Take advantage of them, and there's so many more. If you need to reach out to me, please do, because I'm a big app fan, and even if I have to give a demo, I will, okay? I do it quite often, so thanks for the questions.
Another question we had was, for EEV, is the position of temperature sensor similar to EXV bulb? It is.
The EEVs are going to be different on that. That's going to be done by pressure transducers and thermistors, okay? So it's going to be slightly different, okay? It's not really going to be a bulb per se. The EEV will actually go back into an EEV controller. And I didn't have that slide in there because I didn't want to get into too much. I was afraid to run over. But that will actually go back to a controller, a superheat controller, and it's based on pressure transducers and thermistors, okay? So the thermistor is similar to the bulb. Yes, it'll be clipped on there, very similar. And if you work in geothermal, I did quite a bit of that back in the day. You see a lot of thermistors on geothermal units. And basically, it's just as you all know, I don't need to tell you technicians this, it's just clipped on the refrigerant line detecting the temperature, but it's sending it back electronically as opposed to pressurizing that bulb, okay? Good question.
Another question we had was, how do we cross old compressors that are no longer available and they don't come up on Copeland OPI or the mobile app?
Ooh, boy. Ooh. Boy, that is such a good question. I don't know if I haven't. I tell you what, that one there, I'm going to have you email me because I'm not sure. I don't know. I've never had anyone ask me that question, and obviously it's a good question. Obviously it's happened to you. So please email me that or send your information through either the chat box or email me at don.gillis@emerson.com, and I will definitely get you an answer. I promise you that. And if you do it today, I'll get you an answer today. Because I'm sure there's an answer out there. Unfortunately, I've never been in that situation where I've not had it come up on Copeland Mobile or OPI. I'm sure it happens all the time, but I'm not aware of it. But I will get you an answer.
Thank you, Don.
Hey,
it looks like that is all the questions that we have for today. As a reminder, a recording of today's presentation will be available to you on our contractor resources and HVACR training pages on our website at climate.emerson.com in a few days. In addition, we'll be providing you with a certificate of course completion following the event in a few days. Thank you for joining us for today's presentation. We hope you can join us tomorrow for input-output devices, multi-flex I/O, and ESR boards. Thank you.